Hello. First of all, thank you very much to the organizers for inviting me to give this talk. I think this is a really interesting and very good format for giving talks at a very creative conference. I'm going to tell you a little bit about long baseline neutrino oscillation experiments, and in particular, the path towards measuring one of the last unknown parameters in our three-flavor neutrino mixing paradigm, delta Cp. My name is Stephen Dolan. I'm a staff scientist at CERN, and I've been working on this field for a while, in particular with the T2K and the Doon long baseline neutrino oscillation experiments. I'll have the opportunity to tell you a little bit about. So let's get started. I want to begin this with just a quick introduction to what long baseline accelerator experiments actually are. And so what we start with is a particle accelerator. We use this to impinge a beam of protons onto a target that then gives us a stream of mesons that we can focus into a decay volume. We focus either pi pluses or pi minuses, depending on the polarity of a set of magnetic focusing horns we produce. They can produce a muon or an anti-muon neutrino beam. So it's an interesting feature of these experiments that we can run in so-called neutrino mode or anti-neutrino mode. Note that our beams are quite wide in neutrino energy. We can't produce monoenergetic beams like this, and so we're forced to have beams with quite a wide profile. The neutrinos are then measured far before any oscillations happen at a suite of so-called near detectors positioned just a couple of 100 meters away from the neutrino beam production point. Here we measure what these detectors are capable of seeing, which is event rates that are a product of the flux. So we can verify that our flux is what we think it is. The neutrino interaction cross section, so how often the neutrinos interact with the nuclei inside our detectors, and any detector effects as well. The neutrinos then are left to travel many hundreds of kilometers. Exactly how far you have to, or exactly what energy the neutrino oscillation maximum happens at depends on how far you let them travel. So what the neutrino oscillations actually depend on the ratio of the travel distance, the so-called baseline, and the neutrino energy. And so you can see that the oscillation maximum, so the maximum disappearance of muon neutrinos, is at different points for the Doon, the NOVA, and the T2K experiments in this plot showing the oscillation probability here. And then the neutrinos eventually reach our far detectors. Now, no matter how hard we try to focus our neutrino beams, beams still diverge a little bit, and so we lose many orders of magnitude of neutrino beam intensity as we go from the near to the far detectors. To make up for this, we need our far detectors to be much larger than our near detectors. And this is indeed what we build. So these are enormous detectors. An example, one that I've shown you from the currently operating T2K experiment, it uses the 50 kiloton Super Kamiokande water Cherenkov detector as its far detector. So these really are huge. Here we measure, we want to measure event rates again, but this time we're going to measure event rates of an oscillated flux. So you can see here that after oscillations, we expect a small appearance of electron neutrinos and a large disappearance of muon neutrinos. We actually have a large number of tau neutrinos, but we can't easily see these because of the large tau mass, although we do have some dedicated programs to study them. The two primary event rates we measure are these. So here we can measure muon neutrino event rates or electron neutrino event rates. And what these give us is access to the muon neutrino disappearance oscillation probability and the electron neutrino appearance oscillation probability. I can show you some actual data from the T2K experiment to give an idea about then how we can extract some oscillation parameters from this. So you can see the T2K muon neutrino disappearance event rate. So we started with a Gaussian-ish muon neutrino flux with a long tail. And then what you can see here is neutrino oscillations distort this to give us this dip in the middle of it. That's where the oscillation maximum is. And the depth of this dip tells us about the so-called theta 2-3 mixing angle in our three-flavor PM&S neutrino mixing framework. And the position of the dip gives us information about the large mass splitting. So this is the mass difference between the two heaviest neutrino mass states. We can also measure, though, electron neutrino appearance probabilities, and you see these on the right. Now, note that the scale of the y-axis is a little bit smaller. Over the whole history of T2K operating for more than 10 years, we've only seen of order 100 electron neutrino appearance events. So this is a statistically challenging measurement. The amount of electron neutrinos that appear overall, it gives you sensitivity to this theta 1-3 parameter. And the difference between the electron neutrino appearance you see in neutrino mode and in anti-neutrino mode gives you sensitivity to delta Cp. I should point out, though, that we can combine our results with other experiments. In particular, reactor neutrino experiments can give you a very tight constraint on theta 1, 3 that allows you to actually get a good constraint of delta on delta CP in even only measuring neutrino mode, because we make use of our three-flavor mixing framework. Okay, so if we move on from here, I want to just say a little bit about what our precision on all of these oscillation parameters actually looks like. So I've listed all of the parameters that we have in this three-flavor framework. And I'm showing you how the constraints on them has improved since 2016. So in 2016, you can see we actually do have a few percent precision on a few of the parameters, but this sine squared theta 23 parameter and delta CP have large uncertainties still. If we jump forward to 2018, you can see that now we're really lowering our uncertainties on lots of the parameters. This is where the currently operating T2K and NOVA experiments start to enter a relatively high statistics era. And then when we go to 2022, we've actually got tight constraints on all of the parameters other than delta CP. However, that said, even with this relatively wide constraint on delta CP, we can still put this all together to make some meaningful statements about CP violation in the the lepton mixing sector within this three-flavor framework. And T2K in particular published a paper that made the front cover of Nature here, which was able to exclude the CP conserving values of delta CP at between 2 and 3 sigma. So this is really entering the realm of precision neutrino oscillation physics. But I'm not going to just leave you at 2022. We've had news since then as well. So in 2023, there was a joint analysis between the T2K and Super-Kamiokande experiments. Now, I told you Super-Kamiokande is the VAR detector of T2K. So what do I mean by a joint analysis? Well, Super-K is also an experiment in its own right that measures atmospheric neutrino oscillations. And we can combine this analysis with the analysis of T2K's beam neutrino oscillations in order to build an even stronger analysis by combining the two together. Overall, what this allowed us to achieve is slightly stronger constraints on delta CP and the neutrino mass ordering. So whether the large neutrino mass state is the large neutrino mass difference between the two heavier mass states or the two lighter mass states. And we've got a tighter constraint on those things with respect to the T2K only analysis. We find that we exclude CP conservation within the PMNS mixing framework at about 2 sigma. This is represented in this plot below here, not looking at delta CP, but instead looking at the parameter J. This is the Jarlskog invariant. Now, this considers all of the oscillation parameters to give an overall metric for the size of the CP violation in neutrino mixing. And the key thing is if we can exclude 0, then that's a sign that we've got some CP violation. And you can see that we do exclude 0 at about 2 sigma. The plot on the right then shows you our constraints on the theta 2, 3 parameter from T2K and SK combined compared to the 2 experiments alone. And indeed, you see we get constraints that sit in the middle and are slightly tighter, which is good. But you also see the difference between the solid lines and the dashed lines, which give us our relative preferences for the normal and inverted neutrino mass ordering. And we prefer the normal mass ordering. We can make a relatively meaningful statement of with a 90% posterior probability. So we're honing in on the mass ordering a little bit, I think. Now, in 2024, we have another joint fit, but this time not from T2K and SK, but this time from T2K and NOVA put together. Now, this is a very complicated analysis since these experiments use totally different analysis frameworks. So the correlations of parameters in this is only the oscillation parameters. We can't correlate all of the systematic uncertainties in a similar to the way that we could for T2K and SK, just because this would be much more complicated. But this is the first iteration of such an analysis. And what we find overall putting this all together is that we find that we don't have any strong preference for the mass ordering, but we find that we can exclude the CP conserving values of delta we can exclude CP conservation within our three-flavor mixing framework at between 1 and 3 sigma. Now, this differs depending on if we assume a normal mass ordering, then we exclude the CP conserving the CP conservation at about 1 sigma, and if we assume an inverted mass ordering, it would be 3 sigma. We also, these 2 experiments put together, both make quite precise constraints on the large mass splitting, the delta M squared 3-2 parameter here. You can see the relative constraints from each in the bottom plot, in the bottom right plots there. And you can see the constraints together as well. And these constraints together are reaching a very precise order percent level precision determination of this parameter. Okay, So that's the story so far, but there's still some way to go. Whilst it might look like we're constraining all of these parameters and then that's kind of job done, and we've got much more to do than just to dot the I's and cross the T's. There's we're really entering a precision era of neutrino oscillation physics to let us make a whole set of new measurements. So one thing we can try to do is to make precision determinations of this sine squared theta 2, 3 parameter, as if it looks like it could be potentially taking values to facilitate a maximal mixing, so a complete disappearance of muon neutrinos in a muon neutrino beam at some energy. And this could, a complete maximal mixing might be a hint of some symmetries, maybe feeding down from some gut scale theory. We also want to be able to say for sure, to be decisive in saying that, okay, we think within this three-flavour paradigm, we really do think there's a new source of CP violation. If we get to that, then this certainly has implications for cosmology and leptogenesis, fulfilling one of the Sakharov conditions as it does. And then we can also determine the neutrino mass ordering. As you saw, we're honing in on this, but aren't quite there yet. And so we hope to be able to confirm whether we have normal or inverted neutrino mass ordering. But really, maybe where things get very exciting is the prospects for us to potentially leave this three-flavour framework and explore physics beyond PM&S neutrino mixing. As a hint of the types of things that maybe is just interesting to look at, is that the CKM matrix with very small off-diagonal elements really looks totally different than the lepton mixing matrix. And maybe there's a sign that there's some deeper physics going on here that we can begin to probe through really testing the three-flavour mixing paradigm from PM&S. So in order to do this, we can't do it with current experiments. We need higher statistical precision, and this will come from our next generation of experiments, Hyperchemiocande and Dune. Now, these experiments are exceedingly complementary to one another. They operate using quite different technologies, using different neutrino energies, using different baselines. So you can see to begin with, the Dune experiment has a much longer baseline, and it also operates at a higher energy flux with a very wideband neutrino beam, whilst the Hyperchemiocande experiment has a neutrino flux that peaks right at the neutrino oscillation maxima. They use different technologies, as I said. So Hyperchemiocande uses water Cherenkov detectors, whilst Dune uses liquid argon time projection chambers. They have vastly different far detector masses. But you might say, okay, look, it seems that Dune operates over a longer baseline and has a smaller far detector. How can it be statistically competitive? And the answer is it just has an extremely powerful neutrino beam, meaning the statistics that we expect from Dune are comparable to what we expect for Hyperchemiocande. So you can see you're expecting to see about 2,000 electron neutrino appearance events compared to our order 100 now. So it's a huge improvement. I said I'd talk about constraints on delta CP in this talk, and so here they are. I'm not going to talk through these plots in great detail, but what they do is show you your ability to exclude CP conserving values of delta CP as a function of the exposure of the experiments. On the plot on the left with Hyperchemiocande, you can kind of look to the most optimistic line on this plot. The width of the lines is about systematic uncertainties, and the different colors depend on what the true value of delta CP is. But if it really is maximal and we get our systematics under control, you can be looking at 5 sigma measurements in between 2 and 3 years of Hyperchemiocande running. As a similar plot on the right for Dune, but without the systematics, that also shows an ability to reach 5 sigma constraints on delta CP. So these experiments are very well set up to make these measurements. But really, these experiments are not just machines to measure the delta CP. They are not just PM&S measuring machines. These are new high-energy physics mega projects aiming to complement the Collider physics program and trying to push back the frontiers of particle physics. You can see the relative improvement in the statistical precision we expect between TDK on the left, and I'm showing an example from Dune, but it will be even stronger from Hyper-K on the right. And so these are really these facilities for exploring beyond the standard model. We know neutrino oscillations giving neutrino mass is already beyond the standard model, but now we want to see, is there something beyond that? Is PM&S all there is? And so these huge statistical precision will enable us to be able to look at this. So you can look for, if you see a little wiggle, is this wiggle really the wiggle that's predicted by PM&S mixing, or is there something more to it? With the statistical precision we have, we hope to be able to do this. We also hope to see, so in seeing these deviations, it can be opportunities to see new physics to create these deviations, in particular as an example from so-called non-standard neutrino interactions. And we can really, though, look to physics beyond PM&S more explicitly. So one really neat ability, a thing that we have in our pockets is the fact that we don't only have these experiments, Dune and Hyperchemiocande, These sit in some particular region of baseline versus neutrino energy phase space. But we've got other experiments all around here as well. And by combining the results from these experiments, we can really test PM&S. So one example is you can make constraints, you can make measurements of the say the theta 1,3 parameter using reactor neutrino experiments, and then with long baseline experiments as well, and put them together to see if you measure the same value. If you do, great, PM&S seems to be holding. If you don't, well, you found potentially some new physics. You can also try to make direct unitarity constraints, actually try to measure the row normalizations of the elements of the PM&S mixing matrix. And the long baseline neutrino oscillation experiments can play an important role in being able to tighten our unitarity constraints in a few of these different channels. So in order, though, this is all very exciting, but in order for these experiments to operate successfully, we need to make sure that the statistical precision is matched with systematic precision. We can see the statistical precision of current experiments here, looking at a couple of 100 events in our different channels, with about a 5% systematic precision. And you can take the square roots of these numbers and see that, okay, this is fine. But if we look to the next generation of experiments, you see now we're looking at tens of thousands of events or thousands of events, depending on which channel we look at. And we can look at 5% statistical precision and say, oh dear, this needs to be more under control. And so we find that the largest uncertainty that we have from our neutrino from systematic uncertainties is related to our naivety of neutrino nucleus interactions. Our neutrino cross-section models limit us. And so what we need to be able, and indeed they cause the width of these bands we see in the Hyperkamiokande plot here, that can change our ability to make measurements of or inferences of CP conservation by up to a decade, or just prevent new measurements altogether. So overall, it's crucial to reduce uncertainties, and especially those related to neutrino interaction cross-sections, for these experiments to reach their extraordinary goals. Now, I don't have time to go through all of this in this talk, but suffice to say, there's a whole set of efforts going on to try to constrain these uncertainties sufficiently by combining the nuclear physics theory with experimental neutrino cross-section measurements. And I just want to make one last point, which is that Wolfgang Pauli, when he proposed the neutrinos, said that he's just done something bad in proposing a detector, a new particle that can never be seen. But thanks to our latest detectors and our latest beams, well, have I got news for you, Pauli? We've got more than 1 million events in some of our selections at our near detectors of our experiments, or in dedicated neutrino cross-section experiments like Minerva. You can see the data here doesn't look like neutrino scattering data. It looks like nuclear PDF data. It's really very exciting. So I'm going to leave you here with my summary. So overall, long baseline neutrino oscillation measurements are entering a real era of precision. Presently, we've got a few percent constraints on most parameters, and the first significant constraints on delta CP, closing in on neutrino mass ordering. In the near future, we hope to be able to determine the mass ordering and exclude CP conserving values of delta CP if it's large. And in the longer term, to search for physics beyond PM&S, to have a powerful complementary program to the Collider program to pushing back the frontiers of particle physics. Overall, in order to do all of this, we need to get our systematic uncertainties under control. We've made huge progress on this, but do still have some little ways to go. But we expect plenty of exciting new results and a continued exponential growth of the field in the run-up to June and Hyperkamiokande. That's everything from me. Thank you.